Hello everyone. Today we will talk about capacitance. Right? It's typically a concept that you first encounter in electric circuits. So that's the mainstay of any good, mainstay of all electrical engineering programs is you have like circuits 1 and 2. I think also they are called networks 1 and 2. Right, and you encounter a bunch of lumped elements. You encounter the resistance, you encounter the capacitor, and then you encounter the inductor. Right. So those are lumped elements because they don't care about how a capacitor is constructed in space, in 3D space, how a resistor is constructed, whether a resistor is cylindrical or rectangular, whatever it looks like, doesn't matter. What matters is that it's a lumped component that has a value R and it relates voltage across its terminals to current through it. Same thing with a capacitor and an inductor, right? So those are called like lumped elements, right? Those lumped elements are a special case of the distributed elements. It's where you don't look at the resistor as just a relationship between V and I. The resistor is actually a physical thing that has dimension, that has width and length, and uh, same thing with a capacitor. Capacitor could be constructed in many different ways in three-dimensional space. Right. So that when we study elements as distributed elements, that is the realm of electromagnetics. Right. So when we're studying capacitance at this point, we're studying it in the domain of electromagnetics, which is more general, right? So this is more general than the circuits domain, right? Actually, circuit theory is a consequence of EM theory. So EM theory is the general theory, and it leads to circuit theory. Okay. So from the perspective of EM theory, what is capacitance? Right. So recall that D, the flux density, is epsilon times E. And D, we said, is D and E are measures of the same thing, really. It's like two different, I don't know what's a good analogy of that. It's right. It's like wind, it's like you have a field of wind across the earth, and you measure the wind in two different ways. One way you measure the wind is how much pressure you put a sensor, special sensor, and you sense how much pressure that sensor feels due to the wind. That's one way of measuring the wind, let's say. Okay. Another way of measuring the wind is having like some instrument with a small tube and measuring how much volume of earth passes through the tube. Volume of air passes through the tube. So that's another way of measuring the same phenomena. Right? It doesn't mean that and those two phenomena have those two methods of measurement result in different units, right? So when I measure the pressure, I'm measuring units of pressure. When I'm measuring how much volume is flowing, I'm measuring in terms of volume per second, kilogram per second. Uh, uh, right? So how much matter per second is passing of air is passing through the sensing apparatus. So although I have two different techniques of measurement and the two measurements give me two different units, doesn't mean I'm measuring two different things. I'm measuring the same thing, which is the wind. Same thing with the electric field. I'm measuring the electric field in two different ways. I'm measuring it either through the electric field intensity, which is the force felt by a test charge, right? And E, we said we can describe it as the force intensity, or we can describe it using the voltage, which is, the voltage is just, E is just the divergence, sorry, the gradient of the voltage, right? But it's the same thing, right? And D is, we're measuring it, it has units, V has units of volt per meter or Newton over Coulomb, which are the same thing, right? And D has units of Coulomb per meter squared, and D is a measure of polarization. So it's a different way of looking at the electric field. It's by looking at its effect on the dipoles that are embedded in space itself or in the material itself. So how much those dipoles that are embedded in the medium, how much they stretch and orient, right? So that gives us another way of measuring the same electric field. So we have those D and E vectors that are different facets of the same thing. Okay, and we have this epsilon in between that represents the material. Right? So we could explore the units of E, and we did that in the past, right? So we explored the units of E, and we said the units of E are the units of D divided by the units of E, naturally, right? The units of D are what? Are Coulomb per meter squared, and the units of E, well, I mean, I could say the units of E are Newton per Coulomb, so that gives me Coulomb over Newton, that gives me Coulomb squared over Newton dot meter squared, right? And then that gives me, let me take the meter out, so that gives me Coulomb over Newton dot meter over meter. Right? So we have this special unit here. Right? Let's use the other form for the other unit for the electric field intensity, which is volt per meter. We said we typically use those units instead of Coulomb per Newton per Coulomb, right? Those are more common. So Coulomb per meter squared dot the inverse of the units of E, which are meter per volt. So we end up, again, meter goes with meter, we end up with Coulomb over volt per meter. Right? So Coulomb over volt and Coulomb squared over Newton meter have to be the same thing, right? Have to be equivalent units, right? Because I mean they're measures of the same thing, epsilon. Right? So we established that, and then we said we want to call those two terms, those two units, compound units like Coulomb per volt. We want to call those the farad. So therein comes the special unit called the farad. So epsilon, we said, is represented in units of farad per meter. Right? But what is the farad really? The farad seems to be some kind of unit that measures capacity, right? That's where capacitance comes from, because it's coulombs per volts. Volts is a measure of how strong the electric field is. The higher the voltage, larger the voltage between 2 points, the stronger the electric field between those 2 points. And coulombs is a measure of how much charge exists in space, right? So if we have larger polarization in space, we have higher or larger dipole moments in space, and those dipole moments have their positive and negative charges. So we have a larger amount of dipole charges existing in space. So it seems to be some measure of capacity where, hey, I give you the electric field strength, and then I show you how much charge appears in space due to that electric field strength. So the ratio between the two, the charge that appears in space over the electric field strength, shows me the capacity within the medium. Hey, if I provide this amount of electric field strength, I get this amount of charge. Right? If I have more capacity for the same amount of strength, I get more charge. If I have less capacity for the same amount of strength, electric field strength, I get less charge. So, right? So it makes sense to think of C over V as capacity. How much charge polarization charge I get per volts, where volts represents electric field strength. So this is the origins of the farad as a unit, and epsilon has units of farad per meter. So this is the concept of capacity per meter or capacitance per meter. But then we can think about an extended object now. So I'm not thinking about just a small region of the medium where if I apply a certain electric field, I get a certain charge polarization, right? Dipole polarization. No, I can think of an extended object. You know, some object where I have you know, either a conductor or two conductors, and I think about if I think about the voltage between those two conductors, and then I think about the charge that exists due to this voltage, right? I can talk about the capacitance C of the extended object. Right? How much charge exists in this extended object due to the applied voltage, or how much, or if I assume that a certain charge exists, how much the voltage would be, right? And by looking at the units of the farad, I mean, I can deduce clearly that that concept, that property of the extended object called the capacitance is just Q over V, right? Because C can deduce that from the units, right? C has units of the farad has unit. This is farad. Farad has units of coulomb per volts, right? Coulomb is Q and volts is V. Right? So this is the capacitance of an extended object. The total charge in that extended object over the voltage. Right? This is the definition of the capacitance. It's a lumped properties. Notice it does not. We do not care about the dimensions of the object, what the object looks like. All we're looking is we're trying to extract some numerical lumped property that is one-dimensional. Right? This is just the total charge over the total. Right? It's like a volume, right? When you talk about the volume of an object, you don't care really about the shape of the object. It's just like a distilled one-dimensional number that describes the object. Right? You can have different looking objects with the same volume. In the same manner, you can have different looking objects that have the same capacitance. An example, right? We can talk about the capacitance of some object, single object, right? But we need to talk about voltage, right? And voltage is always voltage between 2 points. So when we talk about a single object, we're talking about the voltage being from that object, V at that object, let's say object A, to with respect to the voltage at infinity, which is 0. Right? So this is the voltage from the object to the voltage at infinity, which is 0. Right? So in this case, C equals Q, the charge appearing on the object, over the voltage of the object. Right? So we can look at capacitance from that perspective for a single object. If our extended object has like two components, we can talk about, so this is object A and object B. We can talk about the voltage between A and B, right? And then what will happen is that we will have some positive charge on one object and some negative charge on the other object, right? And then C equals Q over V. Okay? Or we can say C equals the magnitude of Q over the magnitude of VB minus VA. Capacitance is always positive. Because we cannot have negative capacitance within the scope of electromagnetics. All right, so so this is the concept. Oh, by the way, when we talk about capacitance, we're talking about voltage difference between two components of the object, right, or the object itself and infinity, right? But this implies that within one element of the object, like say this here, this element, or within each of the components of the object, component 1 and component 2, this implies that the voltage is equal, right? So the voltage is the same on object 1 and the voltage is the same on object 2, doesn't change. So this implies that those objects are conductors. Right? So we could talk about capacitance in extended objects that are not conductors. I mean, it makes sense to talk about capacitance, for example, for semiconductors, but it's always simplest to because we have to find the voltage between 2 points. It's always and the simplest example where the voltage is constant at every point along the whole components of the object is when the components are conductors, right? So we can, if we don't have conductors, we can still deal with it, but it becomes more complicated. We have to start integrating, right? We have to consider, you know, a capacitance for a differential element, and then we have to integrate to find the total capacitance. Okay. All right. So what's the general formula for capacitance? Let's write it down. Okay. So typically, like I said, like I have a structure which consists of two parts, and the two parts are typically conductors, and they look, I mean, I'm drawing them as circles, but they don't have to look like circles. They can look like anything really. Then typically one part has some positive charge accumulated, the other part has an opposing negative charge accumulated. So what happens is that if I have a positive charge here, it attracts a negative charge, so they are in lock with each other. We have the field between them, right? And then we have the scalar field, the voltage, right? So we have voltage at object B, this is B and this is A, and since those are conductors, the voltage will be the same within the conductor and the surface. Will be the conductor is an object that has the same potential across all its points, right? And then we have VA. Then the general formula states that C equals magnitude Q over VB minus VA. Okay, and then we can write it. How can we calculate this in general? We can calculate this by we can calculate the total charge, but by using Gauss's law. So I can draw this Gaussian surface, and then I can say Q is just the surface integral of epsilon E dot ds, right? This is ds. So this is from Gauss's law divided by the voltage. The voltage is just, I mean, we know the formula for the voltage going from point A to point B, point A on the surface to point B on the other surface. So it's just minus line integral, oh, it's not closed, line integral from A to B E dl, E dot dl. Okay, so this is the general formula, and the act of actually calculating capacitor is just a matter of figuring out the charge and the voltage. So the strategy for any extended object is, hey, I mean, assume a voltage, and then with assuming that voltage, find Q, and then do Q over V. Or we could assume Q, so assume that there's a certain charge distribution, and then find V, right? And then find the ratio between them, right? That's all it takes to find the capacitance, and we end up finding that it doesn't matter what voltage we assume or what charge we assume. Capacitance is a quantity that does not depend on the voltage we assume or the capacitance sorry, on the voltage we assume or the charge we assume. It is an intrinsic property of the geometry of the structure and the medium that exists in the structure. It has nothing to do with the applied voltages and fields. It's kind of like the volume of a bucket does not depend on how much water you pour into the bucket. It just depends on the geometry and the structure of the bucket. The most famous kind of capacitor is the parallel plate capacitor, which looks like this, right? So we have an upper plate, and then we have a lower plate. Let me draw the lower plate. Right, and I mean, there could be some material in between the plates, epsilon, or there could be air. I mean, you know, or epsilon naught. It doesn't matter. So the plate has a width and a length and separation. D is the separation between the plates. So the assumption with the parallel plate capacitor is that D is much smaller than W and D is much smaller than L. Right? This allows us to use the approximation of the infinite plane. Right? So we already derived the electric field due to an infinite plane, right, with a charge density on it. So if we assume that the distance between the plates is much smaller than the dimensions of the plates, we can use that infinite plane approximation. How does the infinite plane approximation help us? Well, it helps us in that it results in an electric field that's uniform between the plates, meaning it's only pointing from the positive plate to the negative plate, and the lines are parallel to each other, right? So that's what the infinite plate gives us, right? And we derived already that formula. I'll show you how to derive it again. Right? It's still an approximation though. Why is it an approximation? Because once we get closer to the edges, we start to get like a phenomena called fringing, where the fields are going to start looking like this, right? So this is called fringing. It's kind of like when you have two pieces of bread and you have jam in between, and then the jam just fringes from the sides, you know. I'm not sure if that's what it's called, but right. But anyway, we can ignore this. to get the approximate capacitance of the parallel plate, which is pretty good, and it's pretty good approximation. Okay, so let's do this. Let's put in the, so this is plate 1. Okay. Oh, so remember, what if I have a plane? So remember we said if this is the z-axis, so the z-axis is in this direction, right? And z hat positive is in this direction. So remember, if we said if we have rho s charge density on the plate, so remember we used Gauss's law to find this result. So we said, hey, let me do a surface and then go, this is my Gaussian surface, so it part of it is above the plate, this is S1, and then it goes underneath the plane, and this is S2, right? And then I have E1 above the plate, it goes away, the lines move away from the positive charge, and then I have E2 under the plate. So we said and E is parallel to the sides of this Gaussian surface, so that component is 0. So according to Gauss's law, we said that E1 S plus S1 plus E2 S2 equals rho S surface density times S, right? So S1 equals S2 equals S. It's the same. Assume the same surface, right? S is the surface on the plane itself, right? So oh, sorry. There is what does Gauss's law say? It says that the surface, right, of E dot ds equals rho over epsilon naught. So there's an epsilon naught here. Okay. So let me erase this. So I'm just stating Gauss's law here, right? So S cancels with S, and then from symmetry, E1 and E2 should be equal. So it just should be 2E. So E1 equals E2 equals E. Right? They just E1 and E2 just vary in direction, but they should be equal. So this equals rho s over epsilon naught. So E, the magnitude of E equals rho s over 2 epsilon naught. We derived this already, right? So so I can write the electric field here as follows. So I'm assuming the plane is at z equals 0. That tells me that E equals rho s. So I've derived it here, rho s over 2 epsilon naught, rho s over 2 epsilon naught, or yeah, z hat, or this is if z larger than 0, or rho minus rho s over 2 epsilon naught z hat if z is less than 0. Okay, so the field is either in the z hat direction or the minus z hat direction. Okay. What happens if I have a parallel plate? So I have two finite planes that are parallel. Okay, so what happens outside the plate? So on top of the two plates and on the bottom of the two plates. So on top, right, so we have here on the top, we have a positive charge density, and then we have a negative charge density, right? So on top we have two fields, right? We have the field from the positive plate and the field from the negative plate. The field from the positive plate, so E here is going to be, what's the field from the positive plate? It's constant, right? Notice that the field is constant. It does not depend on distance or anything, right? So it's rho s over 2 epsilon naught. Let's assume this is air here, right? There's only material in between the plates, right? And then the field from the negative plate is going to be minus rho s over 2 epsilon. So 0. It's going to be 0. And the field here beneath is going to be the positive component from the positive plate, which is rho s over 2 epsilon naught, and then from the negative plate, minus rho s over 2 epsilon naught. So the two parallel plates have the nice property that the field vanishes outside the plates and only exists in between the plates, right? Of course, minus the fringing. There's some field that exists, that escapes from the sides, right? So here this is rho s, this is minus rho s. So what is the field in the middle here? Again, the field in the middle is going to be the sum of the fields from the positive plate and the negative plate, right? So from the positive plate, we have we said, assuming that the z-axis is this way, positive z-axis. So from the positive plate, we said we had, so remember, so this is in the positive, in this region inside, this is epsilon, material is epsilon inside in the middle. So in this region inside between the plates, right, this is the region where we are under the positive plate. So the field is going to be minus epsilon s over 2 epsilon naught. That's the field strength, right, z hat. And then the region between the plates is going to be above the negative plate, right? So the field will also be negative rho s, right, over 2 epsilon naught, right? So the first term coming from the positive plate is negative because we're underneath the positive plate. The second term coming from the negative plate is negative because we are above the negative plate, right? So this the 2 goes away and we end up with E being minus z hat rho s over epsilon. Sorry, this is epsilon, not epsilon naught, because I'm assuming some material between the plates that is other than air. Okay. So this is the electric field between the plates. I'm assuming, of course, that Z0 is the bottom plate and the top plate is at Z equals D. Okay, I can put in Q now. What is the total charge, right? Total rho s is just Q over A, where A is the area of the top and bottom plates, right? They should match. The top and bottom plates should match, so the area should be the same. So I can plug this in here. So I end up with E, the field between the plates, being minus z hat Q over A, Q over epsilon A. Okay. And then I need to calculate the voltage. The voltage from the bottom plate to the top plate is just minus integral from 0 to D, right? I'm moving from the bottom plate, Z equals 0, to the top plate and calculating the voltage, right? E dot dl, right? And that equals minus the integral from 0 to D. Let me plug in E, minus z hat Q over epsilon A. What's dl vector? Well, I'm moving in the z direction, so z hat dz. And I know how to do this dot product, right? So, and the minus cancels with the minus. So I end up with integral from 0 to D, z hat dot z hat is 1, and the minus goes away and cancels this minus. I end up with Q over epsilon A dz, right? So there is no function of z inside the integral, so I end up with Q over, I can take it out, and then I'm integrating, this gives me z from D to A, from 0 to D, so this is D minus 0. So the voltage is going to be Q D over epsilon A. Therefore, the capacitance is going to be Q over V, Q times the inverse of V, which is epsilon A over Q D. Q cancels with Q, and I end up with C equals epsilon A over D farad. Notice that the capacitance does not depend on the voltage nor the charge. It is purely a function of the material between the plates and the dimensions of the plates. Okay, and this is a typical formula that you would see. It's a very famous formula, right? So the capacitance of a parallel plate configuration is just the permittivity times the surface area divided by the distance between the plates. The more surface area you have, the higher the capacitance. The smaller the distance between the plates, the higher the capacitance. Right? So this is interesting. So this tells me, hey, if I want a big capacitance, if I want C to approach infinity, just make D approach 0. Simple enough, right? Well, there's a problem with that from a practical perspective. And what's the practical perspective? Well, I mean, let's say I make the distance between the plates very small. Right? I end up with a very big capacitance, right? But then I cannot utilize that big capacitance. Why? Because what happens is when I make the distance between the plates very small, very small voltage, like a certain voltage, I cannot have a capacitance that's going to run at all required voltages. Right? The capacitance is going to eventually fail at some voltage. So I'm going to get, if I make D approach 0, I'm going to get a very large capacitance, but this capacitor is going to fail at a small voltage. Say I make the distance a micrometer. I mean, I can get a huge capacitance if I make the distance between the plates a micrometer, but then I'm going to fail at a very small voltage. Why? Because of the concept or the phenomena of dielectric strength that we talked about, right? I have a big capacitance, but it's useless because if I apply like a small voltage, I will reach the breakdown of the material, right? Even if I have just air inside, even air is gonna break down an arc. So I have a capacitor that I cannot use. I apply some few volts to it, and then it will arc and it will discharge the capacitor instantly. Right? Even if I use some material in between, this material is going to eventually break down. Right? So I cannot just get any capacitor I want by reducing D. I can reduce D to a limit, right? If I reduce D, the useful voltage this capacitor can operate at is going to go down. And the useful voltage the capacitor or any capacitor can operate at depends on the dielectric strength or the breakdown of the material between the plates of the cap. That's why you don't see capacitors built with air in between. You see capacitors built with special materials in between, dielectric material that allows the capacitor to run at larger and larger voltages. Okay, so in summary, what can we say the general characteristics of capacitance? So we are summarizing here. So it's independent of V and Q, independent of applied voltages and charges. It's more of a property. It is a property of the geometry and material construction of the structure right? And the third thing we can talk about, and we touched about this at the beginning of the lecture, is that we can talk about capacitance of infinite structures. How? By looking or examining the capacitance per unit length. We'll do an example perhaps next lecture or during recitation. What if we have a very almost like a structure that we can consider infinite? For example, transmission lines. Those transmission lines extend for a very long distance, right? We don't need to talk about the capacitance of the whole thing. We can just talk about the capacitance per unit length, per certain, like per 1 meter, for example. That's how we handle infinite structures. Although, intuitively, if we have an infinite structure, it will have an infinite capacitance, right? That's not a useful metric to say, hey, it's an infinite structure, it has an infinite capacitance, right? What's a useful construct is to talk about the capacitance per unit length of that structure. Okay. And we will do an example or two about that. Right. The final concept I want to touch upon, and this is a concept similar to circuits, is that if we know the capacitance of a structure and then we know capacitance of another structure and then we connect those two structures or objects, we can talk about equivalent capacitance, right? And the way we connect structures is either through a parallel connection or series connection of capacitors. And this is something that we've already encountered even in circuits, right? So you can, if I have a structure that has a certain capacitance, and then I connect C1, and then I connect in parallel to it another structure, right? So I could draw it this way, like the circuit way, and then I have a voltage in between, right? Another way of drawing it, hey, if I have this structure with a certain capacitance, and then the other structure with another capacitance, and then I have a conductor connecting those two structures. This is a conductor wire. I can talk about the equivalent capacitance. Right? So this is the voltage between the two. And it's very easy to find what the equivalent capacitance is. The key is the charge, right? So this will have a Q1 and this will have Q2. The total charge is just the summation of both charges. Right? So the equivalent capacitance is just the total charge over V. V is the same. When you have a parallel connection, V is going to be shared between the two structures. Right? So this equals Q1 over V plus Q2 over V. This equals C1 plus C2. So when you have parallel connected capacitors, the equivalent capacitance is just the sum of all the parallel connected capacitors. You know? So this is parallel. Okay. For series connections of capacitors, something like this, right? And then I have V between them, or I could and lumped, and this is lumped circuit model, and then or in the EM extended structure view or picture, I can draw it like this. I can have, this is the first capacitors, two conductors, and then another capacitor, two conductors, right? This is plus Q, minus Q, plus Q, minus Q. Then I have a conducting wire here. Right? The idea here is that the charge is going to be the same. Why? Because this conductor connected with this conductor is one conducting object, and conducting objects typically are neutral. The charges are just separated to different sides of the conductor, right? So if we have a negative charge here, we will have an equivalent positive charge on the other side. So the charges are always equal. So what is charges are equal between the two structures, right? What we can say is that the total voltage is the sum of the voltage between the first structure plus the voltage across the second structure, right? And the voltage across the conductor through the conductor is zero. The voltage difference through the conductor is zero, of course, right? So we can say now that the total voltage is V1 plus V2, right? And then we know that the inverse of the total capacitance is going to be V over Q, right? I want to put V in the numerator. That's why I did the inverse of the capacitance. So that gives me V1 plus V2 over Q. That gives me V1 over Q plus V2 over Q equals 1 over C1 plus 1 over C2. Okay, so for series connected capacitors, the inverse of the equivalent capacitance is just the sum of the inverses of the individual capacitors of the series connection. So this is also a well-known result from circuits, nothing new here. So this is series connection of capacitors. Right? And yeah, and of course, again, from circuits, we know how to handle situations where we have series and parallel connected capacitors. You do the parallel connected capacitors separately, and then everything turns into a bunch of series connected capacitors, and you find the equivalent capacitance. Okay. One thing I wanted to double check is, or press upon is so remember for the for the parallel plate capacitor, let's check the units. So C equals epsilon A over D, right? Do the units make sense? Whenever you drive something, you have to check the units to make sure that the units make sense. So we said epsilon is farad per meter. What's area? Area is meter squared. Distance is meter. So I end up with meter. So yeah, so this is farad per meter multiplied by meter squared over meter. So this is meter squared cancels, and yes, and we get the unit of farad. Okay, this gives us so this is it as far as capacitance is concerned. It is essentially a lumped property of structures and those structures typically consist of conductors plus the dielectric material that could exist between the conductors. And it's a lumped property again. It's kind of like volume, like I said. Like it doesn't matter what the shape of the object is. It's just a scalar quantity, linear one-dimensional quantity that describes that object. And you can have different looking objects that have the same volume. Same thing, you can have different structures that have the same capacitance, right? One interesting thing about capacitance, and this will be the topic of, so we know from circuits that capacitors, they hold voltage, and we know that they hold energy. right? That's from the classical, from the circuits perspective. But now we know from the EM perspective, typically essentially what capacitors do is that they're holding charge for a certain voltage, right? That charge introduces an electric field between the two plates, right? So we can think of the capacitors as bunching, as concentrating the electric field between the two plates, or between the two conductor structures, right? That's why also another word for capacitors are condensers. They are, in a way, they are condensing the electric field within a certain volume, right? And then we know from circuits that capacitors hold energy, right? So it forces us to have the perspective that the electric field itself holds energy, right? There is energy in the electric fields, which might sound, not that weird, right? Because we're proclaiming since day one that the electric field is a physical phenomena, right? And any physical phenomena needs to have energy, right? Anything physical needs to have energy. It's not a fictitious thing, So the concept of capacitance is the first hint that the electric field really is something physical that holds energy, and we will discuss how to quantify the energy that is embedded within the electric field in the next lecture, right? Also, we'll solve some problems, probably during recitation class too. All right, but this concludes this lecture. Thank you for listening, and we will continue next time.